Hey guys, welcome back for another SVSU Math and Physics Resource Center tutoring video. My name is Brendon. I'm going to be your tutor. And for this video, we're going to get into finding the interval and radius of convergence for a Taylor or Maclaurin series. All right, hope you guys enjoy. All right, so let's go ahead, and what we want to do is we want to find the interval and radius of convergence of this Taylor series here. That is f of x is equal to x to the 6th e to the 2x cubed, and it's about the point x is equal to 0. So since it's about the point x is equal to 0, this is actually a Maclaurin series. But we want to find the interval and radius of convergence of this. So this function looks pretty complicated. So what we're going to do is we first need to find the series representation of this function. And the way that we can do that is we can first find the series representation of e to the x. And then what we can do is we can relate this function to this series representation e to the x. Okay, so let's go over to our power series representation. So we know for a Taylor to Maclaurin or a Taylor series, we can have the function f of x is equal to the summation, as n ranges from 0 to infinity, of f to the nth derivative of a over n factorial times x minus a to the n. Okay, so what we want to do now is we want to fill in all of these pieces. So we need f to the nth derivative of a. So let's go ahead and start taking some derivatives. So f prime of x is going to be equal to e to the x. F double prime of x is also equal to e to the x. And then if we go on, f to the nth derivative of x is going to be equal to e to the x, right? And so now we want to find f to the nth derivative of a. So if we plug in this, it's going to be e to the 0, which is equal to 1. So f to the nth of a is just equal to 1. So e to the x is equal to the summation as n is equal to 0 to infinity of f to the nth of a, which we know that's just going to be 1 over n factorial times x minus a, which is just going to be 0 in this case, to the n. Okay, so e to the x is equal to the summation as n equals 0 to infinity of x to the n over n factorial. Okay, so now what we want to do is we want to relate this Taylor series representation or Maclaurin series representation as we want to use this in terms of this f of x here, our original function that we started out with. So we can say x to the 6th e to the 2x cubed is equal to, so I have x to the 6th, so since our series is in terms of n, we can pull this x to the 6th can come out of the series. The summation as n is equal to 0 to infinity of, so now here in our exponent it was just x, but now in our exponent for this one we have 2x cubed to the n over n factorial. Okay, and then now we just want to simplify this. So we have x to the 6th summation of n is equal to 0 to infinity. And then here it looks like we're going to have 2 to the n and then x to the 3n over n factorial. And then now we can bring that x to the 6th inside of our series. So we have the summation as n is equal to 0 to infinity of 2 to the n, x to the 3n plus 6 using our exponent rules, divided by, that's going to be an n. So divided by n factorial. Okay, and so now we have our Taylor series representation of this function. And so now what we want to do is we want to find the interval and radius of convergence of this. Well, just like on our power series, what we're going to do is we're going to use the ratio test. So let me go ahead and get some more space. Insert. Okay. So now, let's go ahead and use the ratio test. So if we remember, well, for the ratio test, what we're going to do is we're going to take the limit as n approaches infinity of the absolute value of a of n plus 1 times 1 over a of n. Or you could just write it as a of n plus 1 over a of n. I like to write it in this form because what we end up doing is just multiplying by the reciprocal of a of n anyways. So this is the form that I like writing it in. So let me go ahead and write out my terms. So a of n is equal to 2 to the n x to the 3n plus 6 divided by n factorial. A of n plus 1 is equal to 2 to the n plus 1 x to the 3n plus 1 plus 6 divided by n plus 1 factorial. Okay, and so now we just want to simplify this maybe one more step here. So this is going to be 2 to the n plus 1 times x to the, looks like 3n plus 3 plus 6. So we have 3n plus 9 divided by n plus 1 factorial. Okay, so now we can go ahead and plug everything into our limit. So we have the limit as n approaches infinity of the absolute value of a of n plus 1, which is the term that we just wrote out there. So that's going to be 2 to the n plus 1 times x to the 3n plus 9 divided by n plus 1 factorial multiplied by the reciprocal of a of n. So this is going to be n factorial divided by 2 to the n, and then x to the 3n plus 6 absolute value. Okay, and then what we want to do is we just want to see what terms cancel out, and we want to simplify this. So we're going to have the limit as n approaches infinity of, so using our exponent rules, we could write this, actually let's go ahead and write this step out. So we're going to write this as 2 to the first power times 2 to the nth power, x to the 9th power times x to the 3nth power divided by n plus 1 factorial. And for the numerator, we were able to break those up using our exponent rules. Multiplied by n factorial over 2 to the nth power, x to the 6th power, x to the 3nth power, and then absolute value. Okay, so now let's go ahead and start canceling some terms. So we have the limit as n approaches infinity of, so we have a 2 to the n that cancels with the 2 to the n. We have an x to the 3n that cancels with an x to the 3n. I have a x to the 9th that's going to cancel with this x to the 6th is going to cancel with 6 of the x's in the numerator. So that's going to leave x to the 3rd. And then this n plus 1 factorial, I'll go ahead and write out this factorial here. So if I have n factorial over n plus 1 factorial, this is equal to n times n minus 1 times n minus 2, and then so on, right? And then this one is going to be n plus 1 times n minus 1 times n minus 2. And then basically all we need to know about this is that all the terms in the numerator are going to cancel with the terms in the denominator, leaving us just with an n plus 1 in the denominator. Okay, so then this is going to cancel, and the factorial is going to cancel. And so looks like we're just left with, let's see, we have 2x cubed, I think that's all that's left in the numerator, divided by, and then it looks like we just have an n plus 1. Okay, and so now what we want to do is we want to go ahead and pull out this 2x to the 3rd. So if we go ahead and pull that out, so it's 2 absolute value of x to the 3rd, limit as n approaches infinity of 1 over n plus 1. This is going to be, we want this to be less than 1, right, for for our ratio test, right? If our limit is less than 1, our series absolutely converges. So if I go ahead and evaluate this limit, I'm going to get 0, right? Because my denominator is going towards infinity and my numerator is staying at 1. So this is going to be 2 to the absolute value of x, absolute value cubed, times 0 is less than 1. So that's going to be 0 is less than 1. So my interval of convergence, right? So this is just 0. So 0 is always going to be less than 1. So my interval of convergence is going to be negative infinity is less than x is less than infinity. And then my radius of convergence is going to be half of the interval, or just infinity. Okay, so that's how you go ahead and find the interval and radius of convergence of a Taylor or Maclaurin series. In this case, what we did was we had a Maclaurin series, and let's kind of just recap what we did. So first thing we did is we started out with our series, and we could relate it to the Taylor series representation of the function just e to the x, right? And so we first found the Taylor series representation of the function e to the x. We then related our function to it, and we got the series as n is equal to 0 to infinity of 2 to the n, x to the 3n plus 6 over n factorial. So that was our series representation for the function we wanted to find the interval and radius of convergence for. We then used the ratio test to find the interval of convergence and the radius of convergence. And after we used the ratio test, we found that this function is, or this series is always going to be less than 1. So that tells us our interval of convergence is all real values of x. And then our radius of convergence is half that, so it's just going to be infinity. All right, thanks for watching.